Chemistry dogs are not making that's not one size. Maybe it's just the So you think it's that the organic chemists are panicking that it's going into inorganic, and the inorganic chemists are panicking that it's going to organic? I don't know.
Well,
I just live here.
and you notice on one side the H's are lowercase, the other side the H's are uppercase. I don't know if that maybe it's not OO, maybe it's OH.
Oh, that is interesting. Yeah. They did all of it in capital letters over here. I don't know, random, okay, we are recording. Random cartoon. All right, here you go.
There's not an early, Dr. Watson.
No, I didn't know about that. There's not a 58 minutes early. I didn't know about that. All right, are we all up there? Yeah, all right. How did I get up? It wasn't you, Andrea? That's hilarious. Apple will be 58 minutes early.
It wasn't me.
It wasn't you, though?
No. I should have created my.
All right, well, that's your freebie for the day. After that, it's yes. All right, so I want you to make sure you got this. Make the compound below from an acid chloride and an alcohol. Show the mechanism. How could you make the acid chloride? What acid chloride would you use? Where did you break the molecule? Between the O and the carbon. Which one?
Double.
Here? Oh, okay. I get what you're saying. Okay. I thought you'd just say left or right. The carbon that's double bonded. Okay. So what does the piece on the left come from? Here is your clue. What will that be? Is that going to be the alcohol or the acid chloride? Okay, so what are you going to put over here? The okay, and what do you want to put over here? OH. Okay, there's your alcohol. Okay, so what is your acid chloride going to be? There's your clue. So what do we have over here on the right? That stuff. What is that stuff called? Can you say isopropyl? All right. What else? On that carbon, right? Okay. Okay, so if you were to do the mechanism, you're going to start here, and where do you go? Where? To the carbon. Which carbon? There are 4. Uh-huh. Okay. And then what do you do?
Out to the O.
Out to the O. Always go out to the O. All right, so now we have too much to draw for me. Okay, so this is now bonded to what? Here's the new bond. I'll make it black. Show it nice and dark. Okay, so what do I have it bonded to? The carbon of the carbonyl. What is attached to this carbon? A single bonded O, a Cl, and the isopropyl. Okay, what else do I need? A negative on the O, because it has how many lone pairs now? 3, okay. What about that O? Are you positive? Not entirely. Okay, at least you're honest. All right, I'm going to make one of these sets black because it came from the black arrow. Okay, so now what do we do? Remember? Take off that H. Okay, how do we do that? There's a couple ways you can do it, honestly, but the easiest one to do, which is just to do it with this and do it within the molecule. Within the molecule is always going to be fastest. But, you know, if you make water do it, it's okay. You got to be careful, though. If you have a lot of water in here, it will hydrolyze this to cover it, and then you won't get your product. So. That O minus to take that. So look what we're going to have now. CH3, benzene ring. Are you ready to do benzene rings? I'm so excited. We got to get to benzene. Okay. O, C, O, CH, CH3, 2, Cl. Okay. So now this O up here has what on it? NH. Okay, what about this O down here? It has 2 lone pairs again. Okay, now remember where we're going. We want to end up here. So what's the difference between this and that? The Cl is gone. What else? You have a double bond O. What else? That H is gone. Okay, so it's not going to do all that in one step. It's going to take a couple. So what are we going to do first? These electrons are going to go down here, and what goes by? The chlorine does. Okay, because the left side is a strong base, the right side is a weak base. Okay. All right, so we're going to get jammed on the slide. Okay, so here is what didn't change. Draw what didn't change. Okay, so now what do I have? Between the O and the C, I have a double bond. Okay, because we took one of those lone pairs and stuck it down there. What can you tell me about that O up here? It's positive. Okay, what happened to the chlorine? Cl minus. It has 4 lone pairs, right? Okay, now what do you got to do? That was a clue. What's the difference between that structure now and this one? The H. So what do we got to do?
Does Cl grab the H?
Deprotonate. Okie dokie. Make smoky. Remember, when you add to a carbonyl, always go out to the O. Out to.
Would that be a synthesis?
Would that could be, yeah. Yeah, synthesis and mechanism. Oh, how could you make the acid chloride? We didn't do that. Elysian Fields. I have no idea where Elysian Fields is. Okay, so how would we make that acid halide? This one right here. What are we going to start with? What kind of compound?
Oh, kind of.
Carboxylic acid. Okay, so what do we use? The one that gets used the most is SOCl2 impurity. Same one that you use for alcohol, that you can use for alcohol. Okay, that's how you make the acid chloride. Okie dokie. Okay, the last, I added that slide. You didn't have that slide, right? I'm not that, not either. Okay. All right, is the last two slides you have are making ethers from alcohols. Basically what you do is you have a little bit of acid in there, and some of the alcohol will get protonated so that you will have water, and then your other alcohol will act as a nucleophile, and you will displace the water. It's that simple, okay? They call it a bimolecular condensation. That means that you're putting two things together, two molecules, and you're losing what? Water. That's what condensation is. Water's coming out, okay? So that's all it is. And I think, oh, I don't have a deal with it. I thought I did. Okay, so first, protonate one alcohol. When you do this, you don't have, you notice it's 2 up there. You don't have the same amount of equivalents of sulfuric acid. Usually you have less of it. Okay, you don't even have a full equivalent. Protonate one alcohol. The other alcohol adds and displaces the water. And then there's one step left. You have to deprotonate. When you deprotonate with the water, you make H3O plus. That says using. That better? Okay, this regenerates the H3O plus, which can then protonate another alcohol. Okay, this only works well for symmetrical ethers. Okay, see that? Well, what means symmetrical? The R groups on both sides of the O are the same. Okay, if I took this plus this, what would I get? Well, I get the methyl plus the ethyl, right? One on each side. But wouldn't I also get the methyl plus the methyl and the ethyl plus the ethyl? That's how come it doesn't work well to make unsymmetrical. Okay? Because you get too many mixtures. And then you have to separate things that are very similar in boiling point. All right, so the Williamson ether synthesis is a little more specific. So you can make unsymmetrical ethers. The one that you made, I believe, in lab was, is it here or here? Is it the top or the side? Which one did you do? I think you did the side. Yeah. Right, because that would be, it was beta, wasn't it?
Yeah, exactly.
Okay. All right. Well, I wasn't there. I just know that you did it. Okay, so the first thing you do is make the alkoxide. In your lab, you didn't do it this way. You actually got to throw in a base because you used something that is a little more acidic than a normal alkyl. That's how come you got to use a base, okay? And that makes your alkoxide ion. Your alkoxide ion can function as either a nucleophile or a base, okay? That's why it works well only for primary halides or tosylates. Okay, now that you know what a tosylate is. If you have a secondary or a tertiary halide, it will act as a base and eliminate. And you'll get elimination major, not substitution. Okay, so this is how you can make those. Okay? Okay. You're going to start chapter 13 today. It's going to take a few days to get to chapter 13. Okay, and this involves something called nuclear magnetic resonance. Okay? Atomic nuclei with odd mass numbers have angular momentum and behave as if they were spinning on an axis. If you are a charged particle and you're spinning on an axis, you generate a magnetic moment when spinning. Do you remember learning about why two electrons go into the same? I mean, they're both negative. It doesn't seem like they should. I think it's weird that protons hang out in the nucleus too. Okay, so what do? They're spinning opposite directions, so their magnetic fields are going opposite, okay? That's how come they'll go together, all right? Only these nuclei can be detected by NMR spectrometry. You can't detect all nuclei, only ones with odd mass numbers, because they don't have a buddy spinning the other way. Okay, so the first one that we're going to talk about is proton NMR, hydrogen. Okay, does hydrogen have an odd mass number? Yeah, what is it? One. One's an odd number. Doesn't want to go to the next one. Okay, the ones that you can do more than these two, you can do proton NMR, which is regular hydrogen, or you can do carbon-13 NMR. There are a couple of differences between them based on their natural abundance. You have a molecule that has hydrogen in it, 99% of it is this one. What are the other things that those hydrogens could be? What is the possibilities? They can not only be hydrogen, they could be deuterium. They could be tritium. What's the mass number of deuterium? 1 proton and 1 neutron adds up to 2. Is that an odd number? No, you don't see deuterium in NMR. Okay? Now, when you look at carbon, what is the most common isotope of carbon? Carbon-12. Okay, what is in the nucleus of carbon-12? 6 what? Protons and 6 neutrons. Notice that? They all got a buddy. They're all paired. Okay? You can't see carbon-12 in NMR, but you can see carbon-13, which is the next most popular isotope. But y'all, it's only 1.1%. Okay, quite a difference from our 99% of proton. Okay, so it usually takes longer to get a carbon-13 NMR, and it can be a little, there's some other unique differences because of the low abundance. Okay, but both have spins of plus or minus a half. Remember doing those little quantum numbers? Good, that's all you have to do is remember that. We're not going to figure them out. Okay. So what we're going to do with these molecules is we're going to take them and we're going to put them in a magnetic field. When you put them in a magnetic field, there are going to be 2 possible spin states, aligned with the magnetic field and unaligned. Okay, if you are aligned with the magnetic field, you are lower in energy than if you're unaligned. Would you agree? That makes sense to you. I'm glad something made sense today. Okay, so what we're going to do though is we're going to force the nuclei to go to the higher energy state. Okay, it's usually referred to as the beta spin state. The other one's referred to as the alpha spin state. That is probably the only time I would use those. But you give it energy, and it will, when you get to the correct specific amount of energy, it's going to flip. Okay, see how it's flipping from one spin state to the other. Okay, it's going to flip. That's how you get it. Basically, we're going to flip our protons. Okay, all right, I want that thing to go away. Picture one there. It is recording, right? Yeah, you wouldn't say pause and all. Let me do this. I'm going to be moving it around the whole night. Okay, the energy difference between those spin states depends on the strength of the magnetic field. So you'll hear people talk about a 300 megahertz NMR, a 600 megahertz NMR. Guess what we have? Neither. We have a 90 megahertz NMR, but it works pretty darn. Okay, so we're down here somewhere. We're down there. Okay. So the higher your magnetic spin, the higher the applied magnetic field, the bigger the differences between the two spin states. Okay. When an energy source that matches the energy difference between the two states is applied, the nuclei absorbs that energy. Okay, absorbs that energy and flips to the higher energy state. That's basically what we're going to do. Okay? I don't know who figured this out or how they got it started. It still kind of blows my mind. Let's see if I can do that. I don't like, was that thing green? Okay, I'm just going to get out of this. Close these. I'm scared I'm messing it up. Okay. Field strength and RF. Spectrometers with stronger magnetic fields require higher operating frequency. A 7 Tesla magnetic field requires a 300 megahertz radio frequency, and a 14 Tesla magnet requires a 600 megahertz radio frequency. So you're going to have magnetic field and you're going to have radio frequency. You're going to keep one constant. You're going to change the other until you get to that specific amount of energy that that proton needs, and it's going to flip and get. Okay? By knowing where it flips, you can figure out things about the structure of the molecule. And that's what we're going to concentrate on, is worrying about how the structure of the molecule works. Okay, so here is a simple cartoon, if you will, of an NMR. Okay, so you're going to put your sample in a sample tube, and you're going to do this in the lab with JZ. You put your sample in a special sample tube. They're skinny, long tubes, like probably bigger than that, but they're real skinny. You're going to put your stuff into a magnet, and it's going to spin in the magnet. Okay, and then you're going to use a computer and follow the directions. Seriously, that's what you're going to do. Okay, and you're going to be able to figure out what your unknown sample is in that tube based on what you get off of it. Okay, one is kept constant and one is varied. You have an RF and an applied magnetic field. In practice, it is actually easier to keep the radio frequency constant and vary the magnetic field, rather than keeping the magnetic field constant, varying the radio frequency. I don't know why that is. That has to do with the instruments, I believe. But that is what we're going to, technically, we're going to be, the instrument does all that for you, okay? Like I say, we're just happy that it works. Okay, so when you look at an NMR spectrum, you're going to get 4 different basic kinds of information. One, the number of signals. The number of signals tells you the different kinds of protons that are in your molecule. The second one is the position of the signals, where they come on the scale is going to be different based on the environment around each kind of proton. Okay. The third one is the intensity of the signals. Is it a big signal or is it a little baby signal? Okay. The intensity of the signals tells you the number of each kind of proton. So if you have 1 proton giving that signal, it's going to be little. If you have 9 protons giving that signal, it will be quite a bit larger, and to a ratio of 9 to 1. Okay, it will actually be that ratio, and you can figure that out from the NMR. The splitting of the signals. Every signal is not going to be one lovely peak, even though the first ones I showed you. You get one lovely peak, but if you have a proton that's nearby, it affects the signal. Okay, and we'll go into how it does that and what things look like. Okay, so with this information, those 4 things, you can figure out a molecule's total structure. Like you could write it out. It just takes a little practice. Okay, are you with me so far? We're flipping protons. We're going to look at them. We're going to talk about each one of those 4 things in turn. Okay, we're not going to get them all through all of them today. Okay, how many signals does each compound show on a proton NMR? In other words, how many kinds of hydrogens are there in each? Okay, so what you want to look for are symmetry elements. Symmetry. So look at that first compound. What is it, that first compound? It's butane. I know it's Friday. All right. Do you see any symmetry in that molecule? Where? Right down the middle. Okay, so if I split it down the middle, do you see that these are the same and these are the same? Okay, how many kinds of hydrogens do I have? Okay, we're not worried about how they look yet. We're just worrying about how many kinds of hydrogen. That's step 1. Okay, look at the next molecule down there. What do you think about it? How many kinds of hydrogens do you think that one? What are you thinking? Do you see these symmetry elements in there? Do you see that if I do this, that these 2 are the same? Okay. Are these 2 the same as this one? They're both methyls, but they're not the same because these methyls are 1 carbon away from an O, and this one is right next to the O. Okay, so you have 1, 2, 3 kinds of protons in that molecule. Okay. All right, now what do you, and I'm going to write some more molecules that we're going to do. What do you think about that bottom one? Hold on. How many kinds of hydrogens you there? 3. What do you see as the 3? The methyl. The CH2. What do you think about those 2? That's the question, isn't it? Okay. Up here, we had all single bonds, didn't we? Do you remember that you can do what around single bonds? Rotate. Can you rotate around a double? No. So this hydrogen is by the bromine, and this hydrogen is not. So this one has. Okay, so you have to look for that. All right, I'm going to give you another compound. How many kinds of hydrogens are in this one? Okay, now, first of all, I drew a stick. If you forget where the hydrogens are, draw them in. Good rule of thumb. Draw in the hydrogens if you're not sure where they are. Okay, so do you see symmetry in them out? That's what you got to look for. Okay, so how many kinds are there? 2. What are the 2? These hydrogens and these hydrogens. Okay, everybody agree? Okay. What do you think about this compound? Anyway, I guess I could. Think about that compound. Okay, tell me the 3. I'm going to start marking them. The methyl on the L. Everybody agree? Okay, what else? This carbon here. But what are we looking at? We're not looking at carbons. We're looking at hydrogens. There's a hydrogen there. That's what we see. Okay, that's 2. What else? These 2, the 2 CH2s. So this one's 3. That makes sense. Okay, what about this one? About that one. Okay. Tell me one, and then I'll circle it.
Both the methods the same on the O's.
Okay. Yes. What do you mean 2 on top and 2 on bottom? Oh, okay. This and this. That's 2. What about these? Is that 2 more kinds? They're the same. Do you see that there's symmetry in this molecule 2 ways? All right, that is not what I wanted. I thought I had some kind of highlighter thing. Isn't there a highlighter? Ah, there it is. Okay, I found it. Okay, so you have symmetry this way, right? These 2 sides. You also have symmetry this way. These 2 sides. So all the ones in the middle are the same. All 4 of them. So these 2 and these 2 are the same. That's the 3rd kind. 1, 2, 3. So there's okay. I'm going to do this because I don't want to leave the page yet. All right. So what if it was close to that, but it was a little bit different? What if we had it like this? See how similar those structures are? Okay, how many kinds of hydrogens are in that? What are you thinking? Okay, who votes for 1? Who votes for 2? Who votes for 3? Who votes for 4? Who votes for 5? Who is not voting? What? At least you're obvious. Honest. Okay, so which? Give me one. Is it Friday? All right, we have 9 minutes. We have 9 minutes to get this down. All right, so give me one of the kinds. Yeah, that's 1. And then you've got these little H's, right? Okay, that's 2. Okay, then what are you thinking? Okay, do you see that there is symmetry through here? Everybody agree with that? Okay, so because of that, these two are the same and these two are the same. Are these two and these two the same? No, they're different. Okay, so you see how there's 4. So if you had an NMR of this compound and an NMR of that compound, you could figure out which one was which. Only by counting the number of segments.
Why did we count the the carbons that have the OCH3 on them? We counted the this class.
Yeah, we did. That was 1, 2, 3. This was 1, this was 2, this was 3.
Oh, the other two.
No, they were the same one. These were all the same. Okay? All right, now I screwed up the circle. I'll let you all fix it. Okay? They're kind of starting to sink in. It's going to take a little practice. All right, what about a compound that looks like this? I keep using O, but I'll stick with it. How about that? How many kinds of hydrogen? What do you think? Okay. All right, tell me one to circle. Yeah, if it's all by itself, that makes life easy. We'll pick that one first. All right, now what about the other one?
Aren't the other 3 the same?
Yeah, they're all 3 the same. Just like when you have a methyl, all 3 of those hydrogens are the same because you're rotating around the bond. All 3 of those are the same. These are also the same. So there's going to be 2 kinds. You feeling better about it? Getting better at it? Okay. Okay, how many different kinds of protons are in the structure below? It's a stick. Just make sure you picked up on that. Don't anybody say 0 because there's no hydrogens written. Oh, that wasn't a choice. Write it down on your paper, put it in the hydrogen, and then pick. All right, are we all there? I'll draw them in and we'll go over it too. Okay, I got 3 answers. Okay. So, this carbon is how many hydrogens on it? This carbon has how many hydrogens on it? This carbon has how many hydrogens on it? This carbon has how many hydrogens on it? Good. This carbon has how many hydrogens on it? Okay. So, did you go 1, 2, 3, 4? If you did not go 1, 2, 3, 4, can you figure out what you did? Did you try to think that the 2 methyls were the same? The 2 methyls are not the same. This one is 2 carbons away from the carbon with the bromine. This one is next to the carbonyl. They're not the same. Okay, so don't go by CH3. Go by the whole molecule. You gotta look at the whole molecule. Okay, see if I got another one. I do have another one. I thought for sure I had two of these.
Oh, we're doing good.
I thought 0 is a choice. Oh, we're 17. I don't know why I was thinking it was going to go to 18. Okay. D. Oh, I hope right. All right. So let's put the hydrogens in, shall we?
Yep.
Just to make sure you all knew that they were there. All right. Do we see any symmetry in this molecule? Smack dab down the middle, right? Okay, so our kinds of hydrogens is going to be this is going to be 1. These are going to be 1. And these two are going to be 1. So the answer is 3. Okay. All right, so practice that will help if you start practicing that. And look at your book. Next week in lab, you're going to do IR. Okay. That's very different from this. Okay, we are absorbing energy and getting a peak. This is flipping. We be flipping. All right, I'll see you. Have a good weekend. Maybe I'll see you tomorrow helping out at the same building.